Hello, this is Mr. Huber. In this lesson, we're going to look at systems of inequalities. So, like systems of equations, it would be two equations written in the same variables that we're going to work with together. Now we're going to see two inequalities written in two variables that we're going to work with together. First, let's look at each of these first two inequalities separately. So we have y is less than 3x. If we were going to graph this, we'll just draw out a quick sketch of a coordinate plane here. We'd have y is less than 3x. We could graph that by drawing through the origin, because it would be like our y-intercept of 0. Then we go up 1, 2, 3, and we go over 1, and we'd have a point there, and we could draw our line through those points. And then we could shade. It does go through 0, 0, even though it doesn't look like it. It's off by a little bit. Again, graphing by hand, not exact. So we might want to test a point like 1, 0 right here. So we test the point 1, 0 and plug that in. We'd find out that it's true, and we could shade then this part of the graph where 1, 0 is located. If we look at that next inequality, the first thing we'd have to do is subtract the 2x on both sides, so that it would give us y is greater than or equal to negative 2x plus 1. So we have a y-intercept of 1, then we'd go down 1, 2, and over 1, and then we could draw our graph through those points and figure out where to shade. So again, this one we could test the point 0, 0. We're going to test a point. So when we test the point 0, 0, we would find out that it makes the statement not true, because we're going to have a 0 is greater than or equal to 1. If we plug it back in to the original, we put a 0 in here for x and a 0 for y. It won't work. So we're going to want to shade the other side of the line, so it would be for here, for instance. Okay. So that's what those two inequalities would look like if you remember back to when we graphed those originally. And then also making sure that we have, whether it's a solid or dashed line. So on this first example, we have y is less than 3x. We're going to want to make that a dashed line, and so that it will not include the line itself. Okay, so keep that in mind, the dashed line that we'd want to make that. All right, the second one's a solid line because it's got the equal to. So now, if we talk about the solution for the system of inequalities, we're going to want ordered pairs that are solutions for both inequalities. So we want something that's a solution for this inequality and this inequality, both. So how can we do that? Well, we're going to graph the two systems on the same coordinate plane and find out where the shadings overlap. Okay? The solution for the system is where the shading overlaps one another. So we're going to see what that looks like when I draw those same two inequalities, but on the same coordinate plane, my same axes, x and y. So I'm going to draw my coordinate plane, and we'll mark off 1, 2, 3, 4, 5. Give ourselves a little bit of room to work with here in these various coordinates for our x's and our y's. So first we're going to graph y is less than 3x. So let's do that one here in red. So again, it's going to go through the origin like we saw, and then we're going to go up 3 and over 1, and then we'd be able to draw a line through that. We could go down 3 and over 1 as well, and we're going to draw the dashed line through there. Okay. If we remember that from last time, and if we recognize up front, we don't have to go back and make that change. So it makes it a little easier than having to go back. So we have y is less than 3x. And then if you remember, we shaded, okay, we shaded this portion of the graph, okay, everything on this side of the line. Now we're going to graph the 2x plus y greater than or equal to 1 equation. If you remember, when we solved that for y, we had y is greater than or equal to negative 2x plus 1. So we have 1 there as our y-intercept. We're going to go down 2 and over 1. We can go down 2 and over 1 more. Okay, and we're going to have a line, that's solid line, going through those points that then we're going to shade. Now for this particular inequality, right, we shaded, if you remember, we tested 0, 0, it didn't work, so we shade on the other side of that, and we're going to go and shade all of this part of the graph. So what we're looking for is where the shadings overlap one another. You can see in this area, it's only shaded for the red graph. Here it's only shaded for the blue graph. Where they overlap is in this section of the graph over here. So this portion of the graph would be my solution for the system. It would be everything along this dashed line, then this solid line, and everything in here where the shadings overlap. If you pick any point in that area that's kind of going over with the greenish here that I'm doing right now, again, anything in this part of the graph, let's actually use, go with a lightsaber. Anything in this part of the graph over here would be a solution for the system. I could pick a point, let's say 3, 2. That would be right here at the end of the lightsaber, 3, 2. If I plug that in, it will be a solution for both of these inequalities. If I pick a point down here like 0, -3, it's only going to be a solution for this inequality because it's only part of what's shaded for that particular first inequality. If I pick a point up here like -1, 6, let's say it would be up here, that would be a solution for this inequality, but not the first one. So the only points that are solutions for both inequalities are the ones over here where they're both shaded. And that's what we want to be able to find when we graph these systems. Let's try a couple here. So examples you can watch, try yourself, make sure you're on the right track. Okay. In this first one, we do need to take the second inequality and make sure it's solved for 0. So I would need to take this and add 3x to both sides. Okay. That's going to give me 4y greater than or equal to 3x plus 16. Divide both sides by 4. I'll get y is greater than or equal to 3 over 4x plus 4. So we're going to graph these. So we'll graph that second one I just solved first. So we have the greater than or equal to 3 over 4x plus 4. So I'm going to go to a y-intercept of 4. And I'm going to go up 3 and over 4. And I'm going to have a point right there. And it's going to be a solid line through those 2 points. And then I could check my point 0, 0 to figure out where to shade on my graph. When I do that, I plug in 0, 0. It's always good, too, to go back to the original inequality you had up here and plug it into the original. So I can plug 0, 0 in there. I found out that's not true, and so I'm going to shade the other side of the line. So not where the 0, 0 is, but the other side of the line, I'm going to shade over here. And now I'm going to take this first inequality. So the first inequality that we had right here, we'll graph that one in blue and see what it looks like. So I'm going to have a y-intercept of -2 and a slope of -1. So I take my y-intercept of -2. I have a slope of -1, so down 1 over 1, right around there. And then I can draw a dashed line through those 2 points, and that would be my boundary. And I have to figure out where to shade. So I could test a point. In this case, I could test 0, 0. If I test 0, 0, I'll find out that that does, in fact, work. And so my shading would be to the side that has 0, 0 right here. So all of this part of the graph that would be shaded. And so where is my shading overlapping? It's overlapping right in here. This would be the solution area of my graph. A dashed line bordering it on this side, a solid line bordering it on this side, and these points in here would all be solutions for that system of inequalities. So let's try another problem that we can graph, shade, and find where they overlap. All right, so both these equations need to be solved for y. So the first equation, if I take that and I divide everything by 3, I'm going to get y is greater than 1 over 3x minus 1. Okay? X over 3, there's a 1 in front of that x, so that's why I get the 1 over 3. And then my second equation, if I subtract 6x on both sides, I'll have -2y greater than or equal to -6x plus 4. And if I divide everything now by -2, remember when you're dividing by a negative to switch the direction of the inequality, and we have 3x minus 2. So pay attention to those negative signs. Those are very important. You want to make sure, especially when you divide by a negative inequality, you switch the direction of it. And be careful when you're dividing negative over negative, positives over negatives. We're giving the right signs on those. Okay, so let's graph those. So we'll graph the second one there. Y is less than or equal to 3x minus 2. So I'm going to put a y-intercept at -2. I go up 3 and over 1, and I can draw a solid line through these 2 points. And then I'm going to take my shading. I could plug in 0, 0, although it might be tough to tell here. It looks like it could go through 0, 0. So it might be better to not plug that point in and check something else. But make sure you're picking a point that's not on the line and checking that. And you're going to find that you would shade on this side of the line if you check a point properly. Okay? And then now we're going to take that first equation, the y is greater than 1/3 x minus 1. We're going to go to -1 for our y-intercept. And we're going to go up 1 and over 3. And then we'd have a solid line, a dashed line through those because it doesn't have the equal to. We're going to figure out where to shade. This one we could test 0, 0, and we plug that in. We'd find out that it does in fact work. So I would shade the side of the line that contains 0, 0. And I could see where my shading overlaps would be in this kind of wedge of the graph here. Okay? And these would be my solutions for that system. All right, now let's take a look at another one here that brings up a couple special cases where we have horizontal and vertical lines. Okay, so x is less than 5. What might that graph look like? Well, let's check that one out. We'll do that first one in blue. X is less than 5. That means we're taking a point less than 5, okay? And that would be if we count by 2's on this graph, because we see we're going to have x is 11. So to be able to get to 11, if I count by 1's, I'd be off my graph. So if I count by 2's, okay, and this would be 2, then 4. 5 is going to be right here in the middle, okay? And x equals 5 would be a line straight up and down. So we're going to graph that as our boundary line and then figure out where to shade. Okay, so first we're going to bring that line and have it be a dashed line right down through there, okay, between 4 and 6. And then less than 5 means we're going to shade on this side of it. Okay, x is greater than or equal to 11. So again, if we count by 2's, 4, 6, 8, 10, 12, 11 is going to be right in here. Okay, and we're going to do that one in red. So we're going to have a boundary line that's solid, okay, right down here. It actually is over at 13. So let me go back and readjust that. Sorry for that. So we're going to go, there we go, a solid line right there between 10 and 12. And then greater than or equal to means I'm going to be shading this side of the line over here. So where do they overlap? They don't overlap anywhere. Those don't overlap anywhere. There's no solution. There's no number that'd be less than 5 and also greater than or equal to 11. So if the shadings don't overlap, there's no solution. Okay, I'm going to change that second equation here really quickly and show what it might look like if we made that a y greater than or equal to 11. Okay, if we made this equation here and we turn that into y is greater than or equal to 11. Now I'll graph that one in red, and here we'd have to go up, again counting by 2's, a solid line like this between 10 and 12, and greater than or equal to 11 means we're going to graph above that. So that would be all of this part of the graph that's shaded. And now we would have a section that's overlapping. This part in here would be numbers that would work. We could pick a point over here, and we'd have an x value that's less than 5. We'd have a y value that's greater than or equal to 11. So these would be the points that have those x and y coordinates that fit those two situations. So make sure that you check where graphs are overlapping. They might not. That means it's no solution. And remember what to do with those vertical and horizontal lines and how to graph those, because we will still be seeing those. All right, now a faithful diversion. Faithful diversion. Where could that be leading us? What is the oldest U.S. national park? Well, the Faithful is a bit of a clue because it's the national park that contains Old Faithful. Here's a nice picture of Old Faithful, a geyser that is a part of the wonderful landscape of Yellowstone National Park, which is located mostly in Wyoming, but a little bit into Montana and Idaho even. It was established as the first national park in the U.S. in 1872 by President Ulysses S. Grant. And aside from having Old Faithful, which it's most known for, it has wonderful wildlife and different diverse areas throughout the park. So the Geyser Old Faithful is pretty well known for that, but hundreds of different species of animals like bison you see there and other great features. So if you ever get a chance to check it out, it's one of the more diverse national parks I've ever been to, and a lot of great different scenery and things to see. So maybe worth checking out if you're in that area. I think you'll enjoy it. All right. Now on to our last example, and a little bit of a different one here because we have a linear inequality and an absolute value inequality. So let's see what will happen in this particular situation. So I'm going to take that first inequality, y is greater than or equal to negative 3x minus 2. It's already got the y by itself. So we're going to graph that like the ones we've been doing. We'll go down to negative 2 on our y-axis. We're going to go down 3 and over 1 for our slope. Okay, and we'll draw a solid line through there because it's got the equal to. So there's our solid line for that graph. And then to figure out where to shade again, you could do 0, 0. Again, it's pretty close there. If you don't want to risk it, maybe 1, 0 would work. But either way, pick a point that's not on the line and shade. And we're going to be shading for this graph all of this area on this side of our boundary line. Okay. And now we're going to take this inequality that's an absolute value. How do we graph that? Remember how we can get our vertex, negative 4, 1. Vertex, negative 4, 1. So we're going to graph our vertex at negative 4, 1 right there. And then we have a slope on either side for our v. Remember, these are going to be v's of 1. There's no number in here, so it's like a 1. So we'll go up 1 over 1 on either side to make that v shape. And we're going to have a dashed line going up 1 over 1 on this side, and on the other side, up 1 over 1 as a dashed line. And now we have to figure out where to shade on that. So when we can test a point, you can test 0, 0. Find out that's not true, so you're going to have to shade not where 0, 0 is located. So we don't want to shade this part of the graph around the v. We're going to kind of go inside of it. Okay, so when we do that, our shading is going to look like this. Okay. And we can see there's shadings that overlap. Even though they're not both lines as the boundaries, one's the V shape for the absolute value, one's a linear inequality, we can still see there's shadings that overlap right in here. And so any point in here would be solutions for both inequalities. Okay, so again, look for where the shadings overlap, and remember how to graph that absolute value inequality along with linear inequalities. And when you have a system of inequalities, we're looking for all points that are solutions for both inequalities. That would be all the points that are being shaded for both of the inequalities that we're graphing.